So earlier on when we were looking at projectile motion, we looked at the velocity v and we broke that down into the y and x directions, and we also looked at the force of gravity pulling it downwards. So, according to Newton's second law, the sum of all the forces is equal to the mass of the object times the acceleration. Now in this case, the only force on the diagram is the weight. The velocity is not a force, because a force has to cause an acceleration, and there's no acceleration, it's just velocity. So, the weight of an object is equal to the mass times the gravitational acceleration, and gravitational acceleration on Earth is 9.8 meters per second squared. That means the sum of forces for this particular instance, the sum of the forces equals ma, and the only force is mg. So that means that ma equals mg, and that means that we can cancel out the m's, which means that the acceleration of the object is just g, the gravity, and that's pointing downwards. So we had no acceleration going horizontally, but this time we do. So if I get rid of all this, now we also have the force of drag. And the force of drag is always going to be going in the opposite direction of velocity. We also know that the force of drag is proportional to the velocity, so you can say that the force of drag is equal to some constant, which we're going to call k, multiply the velocity, and then since it's going in the opposite direction, we're going to make it a minus as well. And as we did with the velocity, since this isn't going straight up or straight across, we want to break it down to the x and y directions. So if we draw a right angle triangle, let's say this is the force of drag, which is, we're going to say minus kv. Well, we're going to say kv for now, the minus doesn't matter. So kv, so this is going to be kv in the x direction, it's going to be kv in the y direction. So to verify this is true, we know the Pythagorean theorem says that kv squared, a squared plus b squared equals c squared, so that's going to be kvx squared plus kvy squared equals kv squared. Okay? So that's going to be k squared vx squared plus k squared vy squared equals k squared v squared. So we can cancel out the k's, because there's k squared on each term, and we get the vx squared plus vy squared equals v squared. Now remember earlier we said vx is going to be v cos theta, and vy is going to be v sin theta, so we can replace these with, so it's going to be v squared cos squared theta plus v squared sine squared theta, and that's going to be equal to v squared. So now we can factor out a v squared on the left side, so we get that v squared times cos squared theta plus sine squared theta equals v squared. Cos squared theta plus sine squared theta is always going to be 1, which means that v squared equals v squared, so that is indeed correct. Okay, so we know that this is correct. We can say that the force of drag is going to be minus kvx in the x direction and minus kvy in the y direction. So now remember, a force is equal to ma. The sum of the forces, the sum of forces is always going to be equal to ma. So we're going to look at that in the x and y direction. So that's going to be the sum of the forces. I'm just going to put x in a circle here. In the x direction equals, well, the only force we have in the x direction, the weight is obviously pointing downwards. So the only force we have in the x direction is minus kvx, because it's going to be the force of drag in the x direction, which we said would be minus kvx. In the y direction, we have the sum of forces equals, so there's going to be minus the weight going downwards, and remember the weight is equal to mg, so it's going to be minus mg since it's going downwards, minus the force of drag in the y direction, which is kvy. So since the sum of forces is equal to ma, that means the sum of forces in the x direction is going to be m times a in the x direction. That means the sum of force in the y direction is going to be m times a in the y direction, which you can verify from earlier. So now I'm just going to ignore this f part, and we're just going to have two equations for the x and y. So in the x direction, we have max equals minus kvx. And in the y direction, we have may equals minus mg minus kvy. Okay, now we can solve these one by one. So I'm going to start with the x because it's easier. We have fewer terms. So I'm going to take this over here. And just to make it a bit easier, I'm not going to write ax and vx, I'm just going to write a and v, but just remember that this is all for the x direction. So this is all going to be for the x direction. Okay? So we're going to say ma equals minus kv. So remember, a is the rate of change of velocity, acceleration is the rate of change of velocity, so that's m dv over dt equals minus kv. Now we need to get the v's to one side with the dv and the rest to the other side. So if we multiply both sides by dt, we get m dv equals minus kv dt. So now we can divide both sides by m to get the m on the right side, and divide both sides by v to get v on the left side, and we get that dv over v equals minus k dt over m. So now we can integrate both sides, so we get the integral of 1 over v dv, and it's going to start at the initial velocity as u to the final velocity v, equals, now k is a constant and m is a constant, so we can pull those outside the integral, so we're going to say minus k over m multiplied by the integral from 0, the initial time is 0, to the final time is t of dt. So the integral of 1 over v dv is going to be ln of v, of the absolute value of v, evaluated from u to v, equals, and then it's going to be minus k over m times the integral, or the integral of dt, which is just t, and that's evaluated from 0 to t. So now we can just put in the values, so we get ln of v minus ln of u equals minus k over m times t minus 0. So we can simplify this a bit using the log laws. So if you have a log minus another log and they have the same base, you can just divide them. So we get ln of v over u equals, and then minus kt over m. So we want to get an expression for v, the final velocity, so that we can integrate it again and get the displacement. So if we exponentiate both sides by raising them to the power of e, we get v over u equals e to the power of minus kt over m. Multiplying both sides by u, we get v is equal to u e to the minus kt over m. And I'm going to put a box around that. I'm going to call this vx because this is an important equation. Oops. So that's our first equation. This is for the final velocity in the x direction with drag. But as you know, velocity is the change in displacement with respect to time. So we can write this as ds over dt equals u e to the minus kt over m. So now we multiply both sides by dt and take the integral. We get the integral from the initial position is 0 to the final displacement is s of ds equals u, remember, is a constant because the initial velocity, there's only one initial velocity, won't change. So we get u times the integral from initial time is 0 to final time t of e to the minus kt over m dt. Now the left side's very easy to integrate, but on the right side we have kind of like the chain rule here, but there is no chain rule for integrals, so we're going to have to make a substitution. So usually you'd use a u substitution, but because we already have a u here, to avoid confusion, I'm going to call it or. We're going to say or is equal to minus kt over m. So now the derivative of or with respect to t is going to be equal to minus k over m. And now we want to solve for dt, so we can replace this dt with something else. So we get dr equals minus k over m times dt, which means that dt equals, multiplying by m, we get m dr over k, and that's a minus. So we can rewrite this. So I'm just going to do the left-hand one first. The integral of ds is just s from 0 to s equals u times the integral. So now we're going to have e to the power of minus kt over m, that's just or. And then dt, we can replace dt with minus m over k dr. But remember, m and k are constants, so we can actually put them outside the integral. So we get minus m, u times minus m over k times the integral of e to the or dr. Okay? And now just to get our limits of integration back, so we need to plug in that or is equal to minus kt over m. So that means we need to plug in the original one. So when t is t, that's just going to be minus kt over m up here. And then when t is 0, that's just going to be 0 down here. Okay? So now we can continue on with the left side. Left side is just going to be s minus 0, which is just s, equals minus mu over k. So the integral of e to the power of or is just going to be e to the power of or, evaluated from minus kt over m to 0, or the other way around probably, I don't know how to pronounce that. Then we get s equals minus mu over k times, so now we're going to have e to the minus kt over m, and then e to the 0 is just going to be 1, so it's going to be minus 1. And that right there is an equation for the displacement in the x direction. So I'm going to put a big box around it, and that's the end of this part, because I don't want them to be too long.